Well, hello friends. Welcome back to the emulator hacking. Today we are going to continue with the user space emulator, and since the last video I've added a whole bunch of x86 instructions, so the CPU part of the emulator is now pretty capable. I can run a lot of instructions, so that means that we can focus on integrating with the operating system instead, which is really like the more interesting part of this emulation stuff, at least for me. So just to show you where we're at, we can execute bin true in the user space emulator, and you can see here that it exits with code 0, like true should. And if we run bin false, it will exit with code 1, because false always fails. So basically we can run true and false now, so we need to move on to something more complicated. So I was thinking we could go with id, which executes all the way up to an unveil call. So that's where we get stuck. So today I think what we'll end up doing is just implementing one syscall at a time, and maybe a few instructions here and there, and we'll just I guess we'll incrementally work out what's needed to make the bin ID program run. So obviously, if you run bin ID, it's supposed to print out my user ID, my username, my group ID, my group name, and any supplemental groups that I'm also a member of. So yeah, let's get that working. And the first thing we'll have to do is add the unveil syscall, because if we look at the ID program, we can see that, yeah, the very first thing that it does here in main is that it unveils a bunch of paths, and then it will also do a pledge. So maybe I guess we can just start by adding those two syscalls. So the way we've been doing the syscalls so far is that we just we have this virtual syscall thingy here, where we just branch on the syscall function ID. So I think we'll just keep doing that for now. And for pledge and unveil, we can be a little bit lazy here and just I was thinking we could just always succeed, just swallow them. We don't have to get fancy. Let me look those up actually. What are the parameters? So unveil has a param struct, and pledge also has a struct. All right. So they have only the first argument, both of them. I'm a little bit unsure how to organize these virtual syscalls, but for now, this is basically the layout. So the important part is how many parameters do we have as inputs. Then the rest we can work out inside of each syscall. So pledge and unveil. So yeah, so let's just have those be stubs right now. We'll just pretend that they always succeed. Later on though, it would be kind of interesting, because I'm imagining that when we're running the user space emulator and kind of hosting an emulated program, it's probably fine to just add the pledges and unveil paths to the host emulator program. Because if we pledge a bunch of things, the emulator itself does not require any special system capabilities, really. So it should be able to run with any pledge promise set. So I think we can just forward these things to the kernel. But for now, let's just stub them out and see what becomes the next thing that we have to implement. Oh, and let me set up an alias early this time. Root home anon shell rc. Change the u alias to bin id. There we go. Okay, See, now we run all the way to the getid syscall. So that's a very easy syscall to implement. It's just a matter of returning my thread ID. So let's put that one here. Hopefully there will be a lot, mostly really easy syscalls, mostly. Although the ID program, it will open like etc passwd and etc group and stuff like that, and it will read from them. So we'll have to do a bunch of things, but regardless, we'll see. All right, so now we made it all the way to an M map. Interesting. So this is pretty cool. So I guess, where are we now? We are, let's see, this is the ID program, and then we are at A4, A39. So that's in, it's written in the M map. Yeah, but who called it? Let's see. Sterlen. Okay, so somebody's calling a map as OS-alloc. Okay, so this is in malloc. Okay, so we're in malloc calling this. It would be nice if we could print out a backtrace, wouldn't it? Like when we crash the emulator, it would print out a backtrace of the emulated CPU. Let's add that, actually. So first here, let's just commit this. So add. Let's stub out some syscalls. This batch adds getid and stubs out pledge and unveil. Add a couple of syscalls. Yeah. For now. Okay, so let's make a backtrace. That would be really, really cool. So I guess we can put that in the emulator class maybe. So dump backtrace, say. And how will that work? It will be emulator dump backtrace. And here, when we do an unimplemented syscall, we'll just like dump backtrace. Boom. And it will print out where we died. That would be really nice. So, man, how is the backtrace stored? I guess we start with the current execution pointer, or the current instruction pointer, because we have to symbolicate that first, and then we just walk the stack frames backwards. So I think it will be something like symbol is, it's going to be string elf symbolicate the current EIP. Oh, I guess I can get the offset from the symbol as well. So let's get that. In case you're like, if you have a big function, it's really nice if we find out like how many bytes into that function we are, right? Because like if you just say, oh, you're in this function, maybe that function is like 8 kilobytes of code. So it's nice to know the offset into the function. And then let's see. So we would just, I guess we can just print it out for now. Just, I don't know what kind of format we should have, something like this. And then here maybe the name, and then plus offset, something like that. Yeah, like that. Oops. Okay, and then this would be the EIP, and then the symbol characters, and then the offset. Okay, and then we have to walk the frames. So the frame pointer starts out at the EBP register, and then I guess like while we have a frame pointer, then we will well, how does this work? Then we have to read out the return pointer, the red putter, which is like where the stack frame would return to, and that's going to be read. I'm going to read a 32-bit value from the MMU at the. This is just a data segment. I should probably make some kind of constants for these later or something. Just read at the frame putter. Is it at the frame putter or 4 bytes into it? I don't remember. I feel like maybe it's here and then the next frame is at the frame pointer. So let's try this. So symbol is melf, symbolicate, red putter offset, and then we print that out. See if that works. And then the next frame putter is a 32-bit read from the stack segment at the frame pointer with no offset. And then we loop around and keep printing as long as we don't hit a 0 frame pointer. So I think this should work in the normal case. And if we get an invalid address, we'll just crash because of that, but that's probably fine. Okay, check it out. So we have an mmap, unimplemented syscall, and then we can see the call stack here. So how cool is this, right? Like it's actually the call stack inside of the emulator. Very, very cool. And I guess we shouldn't print this one out because it makes no sense. So let's see, if red putter is 0, return, right? Yeah, we'll do that because that last frame is bogus anyway. It doesn't tell us anything interesting. Okay. Man, that's that's so cool. I love it. Like this, this would be cool even if we only had the addresses in the backtrace, but like the fact that we can so easily symbolicate them with the executable that we have on hand, it makes it so nice. Very, very good. All right, so let's just add this here. Add emulator dump backtrace. This gives you a nice symbolicated backtrace of at the current EIP. So cool. It all happened so fast. Like I'm actually really in love with this already. It's happening so fast. Okay, so now we need mmap, right? So mmap is going to be a bit of a big thing to implement, but luckily, we don't have to implement like all of it, right? We just need to implement some stuff. So vert mmap params, I guess. So the way that syscalls that have more than 3 arguments, we don't have enough space to pass the arguments and registers anymore at that point. So if you have more than 3 arguments to a syscall, what we do instead is we pass a struct. And in the mmap case, it's a syscall sc mmap params struct. So maybe something like that. Hold on, let's see here. Mmap. So it's one of these things, and it holds all of the parameters. And when we actually make the syscall in the C library, what we do is we just place one of these structs on the stack, fill in all the fields, and then pass the address of the struct to the syscall. So now that we're on the receiving end of a syscall in the emulator, we have to actually deal with this slightly cumbersome interface. And yeah, so let's just deal with it. Mmap, let's see here. So first thing we'll do is we'll just copy in all the stuff from the MMU. So we have MMU.copy from VM, and then we can copy into params from params address size of params. So that this will just like read out from the virtual memory area into the host memory. It's not terribly efficient, but it should do the trick for now. And now we can read everything in here after this. Of course, this is not going to be safe. You can't access pointers still, but everything else will work. So like these are all integers, right? The only problem would be wanting to access the string here because it contains a pointer to a character string. But we'll just skip over that for now. So let's see. I guess now we want to let's just use a simple region again. It's this stupid region. Obviously, we're going to need to add a more sophisticated memory region stuff eventually, but for now, let's just use a simple one. So make simple region. It doesn't have any like read write flags, stuff like that, but those are things we can add later. So we'll make one, and then we need to provide where does it start. So address, and how big is it? That's the params dot size. And we should probably round that up to the page size. Yes, but how do we know what address is going to be? So now we can't call the kernel, because the kernel will give us memory that's like host memory, but we don't want to give that to the emulator program. We want to like give it virtual memory, right? Something that we control. That means that we need a virtual address allocator. So let's just make a really dumb one, like next address, and we'll just start it at 3 fajillion. Okay, and then how does this work? Then we have an alignment attribute here. So I guess we need to, if we make this static, it will stick around. And then fix me, write a proper VM allocator. So the address is going to be, we need to round up to the alignment, if there is an alignment. So let's see. If params alignment, then address is round up the next address to the alignment. And then we're just assuming that the alignment is a power of 2. We're just assuming that whoever's calling us is a good boy about that. Fix me, what if alignment is not a power of 2? We'll deal with that some other time. Okay. Otherwise, if there's no alignment request, we can just use the next address as is. And after that point, we can increment the next address is address plus rounding up the size to the page size. Okay. Yeah, maybe we should have something like this. We'll call them like final address and final size, just so we can keep track of what we end up with here. So final address, and then the final size is, we can compute that earlier. Compute that here. And there we go. We don't need to do anything in particular with this, I think. We can just say mmu add region that, and then we return the final address as the return value from the syscall. And of course, I've skipped over like protection flags, all of these things right now. We're just assuming that this is an anonymous thing. We're not dealing with anything else. So let's add some assertions here, so that like if we have to, if we get some stuff that we don't support yet, then we would at least assert. So we'll assert that the address is null. Otherwise, it's not an. Otherwise, it's like a fixed location, which we don't want to deal with. And then we'll assert that flags has map anon was. Isn't it called map anonymous? Map anonymous, yeah. So we're asserting that it's an anonymous allocation. Okay, let's try that out. That was an early boot crash. I don't know what that was. Okay. So what you doing? We are doing something aggressively here in a loop. The chunked block constructor is running. I think that's probably doing like a memset or something. Yeah. So we're just like initializing a malloc block. And these things are what are they? 64 kilobytes each. So that's quite a few instructions to initialize one of those blocks, because we're like setting up a free list in the block. And as we can see here, it takes a fair amount of instructions to set that up. So I guess, you know what we can do? We can just like not print out the trace anymore, because I'm feeling a little bit confident that it will mostly run anyway, and then we can just turn it back on if we need it. So let's see, bool trace false. Do something like this, or we can put that here actually. If trace, do that. If trace, then do that. Okay, so now we don't have to stare at that anymore, hopefully. And we'll just assume that it works out. Okay, so we did some unveils, we did a pledge, we did a getid, we've done a few mmaps. I'm just gonna hope that the mmap works out. And then we get to a write syscall. And this is so neat here. We can see that we're in the arguments parser. And it's doing like a printf. And we can see it's just so cool. Okay, so let's implement the write syscall. That one does not use a param struct, I think. Yeah, that one's much easier. Much easier to implement. Oopsie doopsie. So it just has, you know what, let's just do it this way. Just has the 3, and I guess we can do read at the same time, because that one is going to come up sooner or later. So write. So that's the file descriptor, the buffer, and the size, buffer size. Wait, maybe I should use nicer types here. So that's the file descriptor, flat pointer for the address, and a SIST for the size. Yeah, it's nicer to type it out a little bit. I don't know why I thought that would be nice. Okay. So to write something out, so we already have a few file descriptors open in this program, right? Like we're sharing the file descriptors with the emulator. So like std out is std out, and so on. So in this case, probably wants to print on std out or std err. So we can just forward the data. The only trick here is that we have to actually fetch the data from the virtual memory, or from the emulated memory. We don't have like a way to get a pointer into the virtual memory, because it's not guaranteed to be contiguous. So we have to use the memory access API just to fetch it out. So let's see, so we'll fetch out a buffer, copy buffer from VM, data size. Okay. And then I guess it's just a matter of saying return syscall write fd buffer data buffer size. I think that might just work. Let's. Oh, we didn't hook it up with a call. We have to call it. Okay, and let's do read at the same time. So read, in the read case, we have to read into a local buffer first. So here we'll like make a buffer. This is not going to be terribly efficient, allocate a buffer every time, but whatever. I'm leaving so many optimizations on the table in this emulator that it'll be like a task of its own later on to go through this and like figure out what are the hotspots and we can optimize. But we're not going to focus on that at this stage. It'll just be fun, low-hanging fruit to find later. So create a buffer with size, and then I guess and red, we'll do something like that. Read from FD into buffer data, buffer size. That actually makes sense. And then maybe we should do something like this. just to be nice. Okay. So if this fails, return the failure. Otherwise, MMU copy to VM to the destination pointer, which we'll call buffer. This can be the local buffer or something. I don't know what to call it. Local buffer seems fine. Okay, so we copy into the virtual memory from the local buffer. There we go, and then we return the number red. Okay, this stuff is really weird. It feels weird to sort of imitate the kernel, but maybe there is a tidier way to do this. It's just not obvious to me right now. But we have plenty of time to think about these things. Ooh, look at that. So we can see that it's printing stuff out and it's kind of getting in the way. Our syscall debug logging is getting in the way. So let's see if we can syscall colon, if we can move that to the debug output instead. That might be nice. Ooh, look at that. This is the help output from ID. He doesn't know his own name. That's probably because we don't set up the stack correctly when we start the program. But that's pretty cool though that we print out the usage. So let's fix up the stack. So we have setup stack. What we currently do is we set up the arguments vector. So it's just a single element vector with a null pointer in it. So I guess it's going to confuse the arguments parser if we don't have argv0. So let's just add argv0. So we can do something here where we do like CPU push string, push a string, and then we push like the, I was thinking we should push it like the name of the executable. Which we should probably store somewhere. We should store it somewhere. Maybe we should even do a base name on it. So we'll do a lexical path of the executable name, base name. Okay, and then push struct needs to become a thing. So let's see, push string. So this is just for pushing a string onto the stack. Let's take a string view actually. And it's not the most like flexibly useful thing, but it's useful when you're building up like the initial stack for the program at least, because we want to push a bunch of strings. Like we're also going to want to push arguments and environment contents. So this will come in handy for that. So now what we want to do is we want to decrement the stack pointer to make space for the string, and we want to make sure that the stack pointer remains 16-byte aligned. So we will just space to allocate round up to the power of 2, string length 16. Okay. Yeah, that'll do it. And then we'll say set ESP minus space to allocate, mem copy, or no, we can't mem copy. We can emulator MMU copy to VM. From string characters without null terminations, string of length. And then I want to null terminate it. So actually, let's make sure that it gets null terminated here. Right, 8 ESP plus string dot length, and we'll put a null terminator there. Oh, this needs a segment selector. There we go. Okay. That's slightly awkward. Okay, so then after we have that, we also need the executable name to come from somewhere. So we'll have a string m executable name, and maybe we can provide that when we're booting up the emulator. So executable name. Sure. And then here we just give in the executable path, which is probably what I should have called it. Path. Yeah, that's a better name. Path and path. Okay. So, so now we push this thing on the stack, and then we need to remember where we store this. This is argv0 is wherever the stack ends up after pushing that. And then wait, so how does this work out? So then we push this, and then here we want to push argv0 as part of the argv vector, and then we can remove one of these alignment bad boys. And then the argc changes to 1, which we should make this nicer at some point, but we can do it manually right now. Oh, okay, and then now we fail with mprotect instead. And we get a nice backtrace, so that's cool. So mprotect and madvice, I think we can just stub those out, and we just, I mean, obviously that shouldn't be like the final state of that code, but for now we can just stub them out to make progress. Mprotect, madvice, so they have 3 params, both of them. It's like the address, the size, and the protection or the advice in an int. So we'll just put those in here. Some nice little assortment of things being added here. So advice, right. And protect. Advice. Okay. This is going pretty okay so far. Just hope that it's going to work. So okay, new syscall missing. It's getgid. Get the group ID. We already have getuid, so getgid is like basically the same shit. Just just get the group ID instead. No problem, sir. So we'll just make one of those, getid, getgid, and let's try again. This reminds me of like bringing up the kernel initially, where I would just go one syscall at a time. So what do we have here? Unimplemented syscall open. Right. We have to deal with open. Okay, let's commit before we deal with open. So let's see, get add -p. This is, let's maybe do the executable path separately. So the initial stack setup stuff, we'll do that by itself. Yes, yes, yes. Okay. Put the executable name in RGB. Yeah. The emulated program can now find its own name in RGB. Pretty cool. That is pretty cool. Okay, and then let's see. So let's just turn off the tracing stuff for now. We'll put that in a commit here. Disable per instruction trace dumps for now. I have with tracing turned on. It's just too slow when doing big operations like initializing malloc free lists. Yeah. Okay. And then just a bunch of syscalls. Implement / stub out various syscalls. Moving forward on getting bin ID to run inside the emulator. Okay, so now we have to deal with open. Open is going to be a bit of work, but that's okay. So open has a struct, I think. Yes, okay. That's fine. So case sc open return vert open arch1. So we will fetch the parameters much like mmap did. Params mmu copy from the params adder. Okay, and then what do we have in this guy? I'm just gonna bring those down here so I can see them. Well, that didn't work out the way I wanted. Okay. So we need to fetch out the path here. So the path is going to be copy buffer from Vim. Oh, this will probably just work actually. So flat per params path characters params path length. Yeah, this thing is going to need a lot of sanity checks and error checks and things like that later. But right now we're just trying to like bring it up and running. We'll add all the paranoid checks later, of course, because I have to keep track of what we're trying to achieve here, right? Like what I want to do, just to remind myself, is I want to build something like Valgrind, and we're really, really making good progress towards that, because if we can run any of our softwares inside of this emulated CPU inside Serenity, then we can just instrument everything, right? At a very, very, very fine level, which is going to be super sweet. So let's see. So we have the path, and then I guess we can say, like, maybe we can just call regular, what is it, open at with path. I don't remember what it's called. Isn't it open at? Open at with path length. Yeah, that's the one. Okay, so then we just pass in the params directory file descriptor, path data, path size, params options. So we're just forwarding the parameters to the kernel here, basically. Why can't I see this thing? Oh, it's a fcuntal.h. All right. Fcuntal.h. No matching. Oh, because of this guy right here. My bad. Maybe I didn't need fcuntal. No, yeah, I did. Okay. Okay, so if that fails, we have to remember to act like we're the kernel, so errors get returned negatively like that. Otherwise, okay. Is it really this simple? I thought this would be trickier. I'm probably missing something here. Probably. Well, I mean, we might want to do something where, like, we don't share the file descriptors between the emulator and the emulated program. So, like, we would create our own file descriptor mapping table and sort of route things ourselves. But for now, we can just share them because it makes things a lot easier if we can just forward these calls to the kernel, right? Okay, so now we're actually failing with fcuntal. So. I guess it's a TTY calls fcuntal. Not a problem, we'll just implement that. Fcuntal. Okay, it has 3 arguments. Yes, it does. All right. So that's a file descriptor, and then it's a, yeah, what do they call that? Oh, it doesn't matter actually. Okay, so call it file descriptor, command, and argument. All right. So can we just forward this straight up to the kernel like that? I guess maybe we should have a whitelist of things that we know we support, because if they're like if this thing contains a pointer, then it's not going to work, right? Like, because the kernel is not going to be able to. It's not going to know that this pointer here points into virtual memory in our emulator. So. We'll do a whitelist, and in this case it's the STTY thing. Although actually all of these things could be on the whitelist. So let's say switch command. because none of these take pointer arguments. But I don't know if one day we might add something with a pointer argument. So let's just do this nicely. So this will be fine, otherwise default. Yeah, we don't support. Yeah, this is to do. I don't know what's up with these boot crashes lately. Okay, so now we are missing the getgroups syscall, which gives us a list of supplemental groups. It has this signature, says count, and then an output array. All right, so let's just add that. Well, this is pretty straightforward work, actually. Just like writing syscall wrappers. Groups. So there's some magic thing about this thing that if you call it with like a null pointer, then you get the number of groups you need to allocate or something like that. There's something here. If the size is 0, then list is not modified, but the total number of supplementary group IDs for the process is returned. Right, so if the count here is 0, then we can just forward to the kernel and it will give us the number of supplementary groups. Otherwise, we have to actually fetch the list of groups from the kernel, so we'll make a buffer. Create uninitialized size is count times size of getid, and then we'll call the kernel and tell it to give us count groups into this buffer right here, and then let's see, and then if there's a failure, it will just return the failure. Otherwise, we will return success, but not before copying out. Copy to VM. This thing here should not be a pointer. Groups from my buffer size. All of these syscalls are starting to like mash together in my head. Oh, did we forget to put it in the table? Okay. All right, now we need lseek. Just more and more. But how hard can it be, right? So lseek is a 3-argument syscall, I think. Lseek int oft and int. Yes, that's right. This whole setup here is feeling like a little bit like I'm not super sure that this is how it's gonna look forever, but it's working right now, so we don't have to mess with it. And since these are all, like, they're just integers, right? We can simply forward all of this to the kernel. Don't need to intercept or interfere at all, I think. And look at that. We got it. It works. First try, kind of. And it looks, yeah, it looks correct too. Like these are all of my groups and everything. That's pretty cool. So like it runs pretty slow, but I think that's probably because of all the debug output. I can't time an alias. Feature request, being able to time aliases. Okay, so time user space emulator in ID. Yeah, it's like 600 milliseconds compared to 21 milliseconds unemulated. But what if we don't print out this syscall colon for each syscall that comes in? Just hypothetically, how much faster would we be? Oh, hold on, let's just see. Okay, so there's no like spam here at all, basically. And actually we can see that it finished in 126 milliseconds. 110, 124, compared to 20. So it's about like 6 times slower than the real thing, but like a 6x, 6x slowdown, I think that's really, really good for like how little time I've spent on this so far. I think that's extremely nice. And we can definitely improve that, but that's not bad at all. So really, really cool. I wonder if we could like straight up profile this thing just like this with our profiler. Will it just work? Of course it works. So where do we spend our time? It just made me curious, okay? Okay, so instruction constructor is the heaviest. Let's see, B. And then MMU doing region lookup for 8-bit reads, which come from the instruction decoder. So huge performance opportunities, obviously, here. And then I wonder what's the heaviest. What's this? Oh, this is like opening the executable. Probably like skip over the first one. I mean, actually, we should include everything because like time spent in the kernel is still relevant. Although it might be a nice feature for the profiler if you could like ignore kernel stack frames or something like that. If you're only interested in user space, time spent. Anyway, so the heaviest instruction that we have is the STOSB, the store string byte. And yeah, so like if you compare here, like this is like a single instruction, right? But we have to do a fair amount of things in C++ to implement this behavior. But we can definitely slim these things down and make them more efficient, for sure. And there will be a time for that. But right now, I'm just super happy with like, I'm going to call it 5x slowdown. Or let's call it 6x because that makes it nicer when we eventually make it faster. Because then the improvement will be bigger. So 6x slower. For ID, at least. I wonder if it can run anything else. It can run cat. Hello. It runs cat. But we can't close. Oh, that's funny. Okay. Run PS. We need the TTY name for that. I guess we can add the close syscall. That's not so bad. Let's just a matter of forwarding to the kernel, I think. So I'll close. Because that really just has one argument, right? Like the file descriptor. So okay. Oh, forgot to declare it. Cat, hello. It just works. Super cool. We do echo. I guess, oh, we don't support arguments yet. That's true. On the yes program. Yes, we can. That's so nifty. We're not going to be able to run anything like more complex, like about. It wants getpid. I mean, yeah, running a GUI program is gonna take so many more syscalls, and we'll get to those because I want to run GUI programs in this thing. Obviously, like the end goal is to be able to run all the software in this thing if I want to. But I guess I can just add getpid just because I'm curious what comes after. Getpid. Fun fact, the getid syscall in the C library actually has a cache to avoid multiple syscalls because the tid does not change. Bit doesn't change either. We could add a cache there too, but this one is just way more aggressively hit currently. So where's getid? Getpid. Still runs, and about now wants to make a pipe. All right. I'm not gonna go all the way here, but like we got ID running. How cool is that? That is just super duper cool. Maybe we should remove that exit output also to make it look completely transparent. That would be really sweet. So let's see. Is there anything here that we want to do separately? I feel like maybe not. Yes. And implement more syscalls. More. Alright. Implement enough syscalls to get in the running. Okay. And then we just have this thing. This thing here where we show the syscall that we're doing. I think we don't need to show the syscall. If it's a syscall that we support, you don't need to print that. So we'll put this behind like a debug spam thing. And then if you want debug spam, you can go and turn it on. I'll put some syscall logging behind debug spam. Okay. So that's really sweet. I think this is going to be it for today's video. This is really nice progress. We didn't have to fix any instructions, which is really nice. It means that the CPU core, soft CPU core, is pretty capable, pretty strong already. That's really nice. It's interesting that like if you do like a whole system emulator, then you end up like having to implement so many instructions. But if you only want to support like GCC compiled binaries for 32-bit user space Serenity, they tend to use like not that many instructions. They use like a tiny slice of the entire Intel instruction set. So that's really nice. Yeah, so let's remove this thing here. Vert exit. We can put this on the debug output instead. Move exit. This is called logging to debug output. We want the emulated program to appear without noise in the terminal. Okay, so now it's time bin ID, time user space emulator. I can't autocomplete here. Transparent execution. Very cool. Yeah, so this will be it for today's video. I don't know what we'll do next time, but I'm super happy with the progress. This thing is developing faster than I thought it would, for sure, but it's really great, and I think we're getting to the point now where we can start thinking about how to implement some of the error checking, bug finding features, like finding uninitialized memory that you're using, like if you're branching on an uninitialized value, stuff like that, and you know, use after freeze, these types of things. We're going to need metadata for those things, and we need to think about how to add that metadata and how to track stuff, but this will be fun. So yeah, if you made it this far, thanks for watching, for hanging out. I hope that this is interesting. It's definitely interesting to me, and I think it's going to be really fun to see what we can do with this. So thank you for checking it out. I'll see you next time. Bye.